21st century skills, these are skills that are supposed to help you, to be competitive and to apply the knowledge that you're learning in the different aspects of your life. And when you gain these kind of skills, then it makes you, very productive wherever you are. So we have skills like critical thinking. You have skills like creativity, collaboration, communication, information literacy, media literacy, technology literacy, flexibility, leadership, initiative, productivity, and social skills. These are some of the main 21st century skills that you really need to keep developing even as you move along. The basics of computational thinking, it is a process of solving complex problems by breaking it down into small component parts and then recognizing the patterns in those component parts, then focusing on what matters so that you can come up with a set of rules on how you can solve a big problem. 4 principles that are involved in computational thinking. And the 4 principles, one is decomposition. Then the second one is abstraction, then pattern recognition, and then algorithm writing. These key techniques will help you to to think computationally through a complex problem or challenge before even writing any single line of code. Decomposition is the breaking down of a complex problem into smaller, more easily solved parts. So that's the first step of computational thinking. You break down a complex problem into smaller parts. So these smaller problems are solved one after another until the bigger problem is solved. Let me give an example. You have, maybe you've been told to add all the numbers between 1 to 200. You're given a problem like that. Now it becomes, if you look at it from the face value, it might look as if it's a complex thing, because now you're starting to wonder, okay, I have to take, 1 plus 2 plus 3 plus 4 plus 5 all the way to 200. If I am to add the 100 all the way to 200, I can take something like 1 plus 200. Now that is going to give me 201. If I take the next number, which is 2, then I add 199, which is the other number from now the 200. So I'm starting with the lowest number and I'm adding it to the highest number that is next to it. That one will still give me 201. If I continue with 3, then I add to 198. That one I will also get 201. If I get to 4, then I add 197. That will also give me 201. Pattern recognition. So in the pattern recognition, what you do is once you have decomposed the complex problem into smaller problems, you need to look into similarities that they share. The patterns which are shared are characteristics that occur in each individual problem. When you observe those similarities, they will help you now to solve that larger or complex problem with more efficiency. Like now in the example I have just given of adding the numbers 1 all the way to 200, after taking 1 plus 200, then 2 plus 199, 3 plus 198, 4 plus 197, I have noted that each of the numbers that I have been adding, they give me 201. So already I'm recognizing a pattern that for the numbers that is the highest and the lowest, that I add, the lowest in an increasing manner and then the highest in a decreasing manner, as I keep adding those numbers, I realize that there's a pattern that is developing. I'm getting to 1 for each one of the numbers. And I can tell that this one, I'm going to repeat this one for about 100 times. because I know that by the time I'll be getting to 100, and then the other number being 101, abstraction. So with the abstraction, it refers to focusing on the important information only and then ignoring irrelevant details. So to reach a solution, we need to ignore all the unnecessary characteristics in order to focus on those that will matter to us. Like now, we had a summation of 1 plus 200 giving us 201. We also had a summation of 2 plus 199 giving us 201. We also had a summation of 3 plus 198 giving us 201. And I can keep repeating that. All those numbers, even when I get to 10 plus 191, which will also give me 201. So I can forget all those other data, like the 2 plus 199, because I know all of them will still be giving me the same result, which is the 201. And then I can now focus on the 201, which can easily be given by 200 plus 1, and then that one can be repeated 100 times, because I know that's the number of times those numbers are going to be repeating in this case. Now I can easily tell you that to do an addition of all the numbers between 1 and 200 can easily be given by 200 plus 1, that one multiplied by 200 divided by 2, which would actually be the same as multiplying by 100. And I can easily get the summation there as 20,100. So 20,100. Algorithm writing enables you to develop a step-by-step instructions on how to solve each of the smaller problems. Now, these step-by-step instructions are what we call rules. And those particular rules now are the ones that you use on a computer to help you to solve that complex problems in the best way possible. So we say an algorithm is a plan, a set of step-by-step instructions used to solve a problem. For me to solve the problem of adding the numbers from 1 to 200, the first step would be to take 200, then I add 1, because that is one of the things I identified. Then the next step is to divide 200, which is the highest number, by 2. And then the third step is to multiply the result of the step 1 with the result of the step 2. That would be 201 times 100. And that way, I basically solved that problem that I had, which was an addition of all the numbers between 1 to 200.
Computational thinking. What is it, and why is it so important? Let's start by looking at the what. You may think that computational thinking is about thinking like a robot or programming like an expert. But it's not. Rather, it is a very versatile skill, a skill that focuses on critical and logical thinking. To put it simply, computational thinking is a problem-solving skill. Let's dive a little deeper. Computational thinking is about looking at a problem and solving it systematically, and therefore arriving at a solution that both humans and computers can understand. Essentially, it is considered the highest order of problem solving. Computational thinking is made up of 4 elements: decomposition, pattern recognition, abstraction, algorithmic thinking. First of all, decomposition. Decomposition is about breaking a difficult problem down into simple and easy-to-manage parts. Second, pattern recognition. Problems come in all shapes and sizes. But amongst their many differences, there are bound to be similarities. Pattern recognition is about spotting what different problems have in common and using what's worked before to help you out again. Third, abstraction. Abstraction is all about focusing on the details that matter while ignoring the ones that don't. By applying abstraction, we can cut through fluff to get to the heart of the matter. Finally, algorithmic thinking. Algorithm is really just a big word for a set of rules. So algorithmic thinking is basically when you generate a series of simple steps that anyone can follow to solve a problem. Now, let's bring everyone together with a simple example. Meet Max. He's your average hardworking young man, trying his best to be a productive member of society. But today, Max's car has broken down. Luckily enough, he's computational thinking enabled. Let's see how he solves this problem. Max's car can't move too well. He realizes that there are two problems. He's running low on fuel, and he has a flat tire. That's the first pillar, decomposition. Now, Max has been in a similar situation before, and based on past experience, he knows that he should take care of the flat tire first. That's the second pillar, pattern recognition. He doesn't have much fuel left, but it's enough to get him to the next patrol station. So he decides to ignore that and focus on the tire. That's the third pillar, abstraction. Finally, to change a tire, Max has to use a jack to elevate his car, loosen the nuts on his tire, remove the tire, and replace it with a new one. Now that's algorithmic thinking. As you can see, computational thinking isn't just for computer scientists or programmers. In fact, many kinds of people, from mechanics, doctors, to presidents, are subconsciously applying computational thinking in their daily lives. Thanks, Max. Have a nice day at work. So why is computational thinking so important? It's not. That is, if you don't mind being left behind in the Stone Age. According to Moore's law, computing performance doubles every 18 months. That is to say, in 10 years, a $1,000 computer will be able to compute faster, more efficiently than the human brain. With technology growing at such an exponential rate, we are integrating computers more than ever before into our lives. To connect, to optimize solutions, and most importantly, to solve problems. The possibilities are limitless. The problem is, having a supercomputer carry out basic instructions and tasks is not at all economical. To make full use of a supercomputer, you'd need to know how to give super instructions. This is where computational thinking comes in. A powerful way to generate advanced solutions and manipulate computers to work for you. Now, imagine if mankind had such immense power at our fingertips. We would be solving problems faster than ever before.
When you practice with the scratch.mit.edu and microbit, I know this is going to help you to understand all these other things and the concept we are going to be talking about.
Introducing Scratch. All the games in this book are made with a programming language called Scratch. Scratch is easy to learn because you don't have to type any complicated code. Instead, you build programs from ready-made blocks. Getting started. A project in Scratch usually starts with choosing what objects or sprites you will appear in the game. Scratch has a large library of ready-made sprites to get you started. Sprites. Sprites are the things that move about or react in the game. They can be anything from animals and people, pizzas, or spaceships. You can bring each sprite to life on screen with a list of instructions called a script. Scripts. Scripts are made up of blocks that you can drag with a computer mouse and join together like jigsaw pieces. Each block contains one instruction, so it's easy to understand. Working together. Games are usually made up of several sprites working together, each controlled by their own script. Scripts make sprites move about, crash into each other, create sounds, and change color or shape. Some sprites act as enemies to make a game more difficult. A typical Scratch project. Once you've built a script, you can click the green flag to see what it does. All the action takes place in a part of the Scratch window called the stage. Sprites move about on the stage, often in front of a background image that helps create atmosphere. Running a program. Starting or running a program activates the scripts that you've built. To make the stage fill your whole computer screen, click the blue symbol on the top left. To stop a program, press the red button on the top right. Making sprites move. In a typical game, the player moves one sprite and the other sprites are programmed to move automatically. The script below makes the dinosaur in this project chase the cat. When the green flag is clicked, the dinosaur will point to the cat. Move forward 15 steps. Adding the forever block keeps the sprite moving endlessly.
This is the main window that you get, and it has the different bits that you can have. So one, we have the code, and we have the different blocks here which are given. So this is a block for the motion. If I click on the looks here, you can see the different blocks for the looks. If I click on the sound, there are the different blocks there for the sound. If I click on the events, there's also the different blocks of code for the events, and you can keep checking in one of them. Then sprite, and the sprite becomes the element that you're using for any particular time. And you can decide to choose which kind of a sprite you'd want to have. So for now, we have the sprite one, and I can click on this to choose another one. Like now, I can just do a quick one where I'm going to bring this block of when clicked. So I want to use this one to run, which is written here, the go, and then there is the one for the stop. So when I click the one for the go, when clicked, so I want to say what is going to happen. Now you can see the sprite that is selected is this one. So that way you can see it's even the one that is highlighted at this part here. So when I click the start, so what I want this one to do is probably have some motion. So I just go to the motion, and then I say move 10 steps. So from where it is going to move 10 steps. And I can even demonstrate that one by clicking on this. I can even add the steps here to be something like 100. Then I click on that. I want also to play a sound, and you can see there is the sound that is even selected here. So if I click on the start, you can see it is still moving, and then as it is moving, then it is also giving the sound. I want to keep before maybe it plays the sound, I want to wait for 1 second after it has done a movement. I can also decide that I want this one to be repeated over and over. So I want this one to be repeated. So it will always be moving 100 steps. It gives a sound, then waits a second, gives a sound, then continues. I can have something like that.
Today I'm going to demonstrate how to program using the block, also known as drag and drop programming. There are several editors in programming languages such as Scratch and Snap, but today I'm going to show you how to use the microbit editor. You can go to microbit.org/code and click on Let's Code. To the left, you'll see a microbit simulation. In the middle, you'll see block categories, and then to the right is where you drag your blocks and start your program. I'm going to demonstrate how to do a very basic program. If you go to Basic and drag the unstart block and drag it onto the right side. Then we will go back to Basic and drag Show Icon. Make sure that when you're dragging the blocks that they're yellow around and then a yellow arrow shoots down. That means that it's on the right spot. Now, as you can see, when your microbit starts, a heart will be displayed. If we go back to Basic, we can click on Forever, and then go back to Basic, and then Show Icon. We can click down and display another icon. So let's display the sword. That means that the sword will display forever. Now, to dispose of your blocks, you can simply click on it and then drag them to the left. And now they're disappeared from your program. Now let's go to Input and drag the On button A pressed. Let's go back to Basic, back to Show Icon, make sure there's a yellow outline, and click down. Now let's click down and select another image. Let's select the happy face. So that means that when you press button A happy face will be displayed. Now let's do the same for button B. Click down here, and you can select B. Now let's go back to Basic, Show Icon, and I will do the sad face. So as you can see on the simulation to the left, there's a heart when it starts. Then when I click A smiley face, and I click B, a frowny face.